Hi, now we will continue with the next part of the lecture when we will talk about differential and common mode signals. And this is quite, or I would say very important topic, because by that you will be able to understand different noise sources in PCBs as whole, completely. And by knowing each noise source, how it is generated, you will be able to minimize it. So, differential and common mode signals. Let's say, for example, we have a source, which is here. That's any voltage source with high frequency signal, such as maybe a video signal, or it could be USB, it could be Ethernet, it could be anything that has high frequencies. And that source, voltage source, is taken, the signal is taken with two lines, and these two lines could be a part of the cable. So let's draw a cable over it. So I will draw a shielding around this, and that would be a single cable with two wires. And this is then taken to a device. Let's say if this is a video signal on your laptop source, this would be the projector on the ceiling of the room. Or this could be a power supply, and this could be your laptop. So it doesn't matter whether we are talking about communication lines or power lines, because also power lines contains high frequency currents, if you remember from previous slides when I showed different sources of EMI. Now here I would like to now start explaining what I meant by that. Now, this input of that device, whatever it is, contains some impedances, and this is impedance between one and other line, which I will call differential impedance. And these are two common impedances, impedance common mode 1 and common mode 2. And these are connected to some case. Now, where do they come from? That one is quite usually the input impedance of the amplifier of some kind. These two could be some capacitances or even resistances between the ground of the whole system and these inputs. It could be either intentional values, intentional components put in, or they could be stray capacitance or stray impedances actually. So all that is possible. Nevertheless, there is now an idea of a third path. Now that current in that cable, that one here and that one there, are in principle the same. If the current runs in that wire and returns back through here and runs back, that would be called a differential current. That's differential current. Now, what if a small portion of that current runs also through here and here? Where does it return then? Well, it returns then back somewhere else. And this somewhere else could be, let's say, here. So, how does this path become? How is it possible that the current returns back on some third path, even though there is no cable there? Well, the reasons are several. One of the problems, or one of the reasons, is that this case of that device is grounded. And the source is grounded as well. Then we surely have a third path on that ground connection. What if we have floating device, so that there is no ground here and there is no ground here? Then this connection can be actually done through the air. So actually here we can have a big capacitor, which is represented by the space around. And that capacitor, I said big capacitor, actually the capacitance is very small, but dimensionally it can represent the whole room. So there is a capacitance path also present through the air. And this return current can escape through that as well if it contains high frequencies. So if you have a third current, you can divide this current into two portions. You can say this current is actually a combination of common mode and differential mode current. So if these two currents are now not the same because there is a third path running back through these paths, then you have a difference between I1 and I2. And having a difference between these two means that if you sum them up, you will get a differential current. So I differential current, EDM differential mode, equals to sum of these two currents by half. So the average value of these two currents. The common mode part, that one that runs here, is a difference between these two currents divided by 2. Now, you can, in such a way, distinguish or represent these two currents by the common mode part and differential part. And that's the idea behind it. And then you know that the common mode part, the ECM, would exactly be running through the third path, and that common mode part runs in the same direction in the cable. And differential mode part runs in the opposite directions. And these two then represent the whole current I1 and I2. So representing them, we would say that I1 equals common mode plus differential mode. As you see here, they are running in the same direction. And here, the I2 is equal to IDM minus ICM. And that's actually what was calculated here. So let's go now into some examples. Let me show you a power supply I have here. That's a power supply, right? And on the other side, so we plug it in, and on the other side we have a cable, right? And we are putting it into our device that we are powering. Let's say that one. So now, what do we have here? We have a source of the signal, which is actually DC, right? So it cannot contain any noise. We have a cable, which is represented on this picture as this cable with two wires. Let's say there are just two, okay? Don't be too punctual. On the other side, we have a device that we are powering. That's the device there. So if there are any noise sources in this device, then they are containing high frequency parts, high frequency spectrum parts. And there is a third path between these two, even though you can't see it. It's the path through the air. And through that path, maybe, but just maybe, some of these noise currents are coupling back to here. And this is the common mode part of that signal. You notice that? What is on this cable? This fat thing. It's a common mode choke, which blocks these high frequency signals from here to spread along this cable. This is the common mode choke that makes the cable high impedance for common mode currents. How is that done? Later. Good, then we can continue. What does these common mode and differential signals influence, and how do they represent, how they are influencing the high frequency electric field in a certain distance, which is shown here. Now, here I show two cables, or two lines, two tracks, two current carrying lines in a cable. they contain differential mode part and common mode part. As you know, differential part is much larger than the common mode part because the majority of the current runs through these lines here. Now, these two currents, differential mode currents, are subtracting their electric fields because they have the opposite polarity. So their electric fields actually are subtracting at a certain distance. So that means that the portion that is still left for these two electric fields is very small. And it is smaller if these two currents are more similar. And it is smaller if these two lines are closer together and further away. Because the electric field strength drops by the distance from these two lines. And if the distance of these two currents to that certain point is more similar, then this resulting electric field would be smaller. So if you check out these two equations showing the analytical solution of electric field at a certain distance r from the cable or from the two lines on printed circuit board, if you might, then you would see that the length is here, the distance is also there. So length times distance actually means what? Means loop area. This is loop area. This is the distance from the tracks, and we have frequency squared. So frequency squared and loop area. So in order to make, that means for the cables in the free air and from the tracks on the PCB. But in order to make differential noise at a certain distance from the PCB small enough, you have to decrease the loop area of all current loops. So loop area should be smaller, and of course frequency as well. About frequency we already talked about the loop area. That's the new thing now. What about the common mode current? The common mode current is much smaller. And therefore, since it's much smaller than the differential mode, you would say, okay, then we don't have much problems with it. Well, actually we do, because their electric fields are summing up because they are running in the same direction. Therefore, they are not canceling each other. And their electric field at a certain distance, it's not related to the area, but it's just related to the frequency here and the length of the cable. So keeping the length lower and keeping the frequency lower, and of course, which is also important, keeping the common mode currents lower would then make it less EMC problem. Okay, so now we can go into the real example. Here I show you an example of a PCB that contains a small current loop and a cable. This small current loop is of 1 square centimeters large. So that's the area of the loop. It runs at 100 megahertz and it contains 1 milliamp of current. So there is a small loop here. Let's say that one here. Oh, come on. That one. It is a 1 square centimeter large with a 1 milliamp of current at 100 megahertz. The electric field at 1 meter distance, according to the equations before, would be 26 microvolts per meter. Changing it to a decibels, you would get 28 decibel microvolt per meter. How much is that? You wonder yourself. Well, that's quite a lot, even though it seems very small. We will show you very quickly. So 1 milliamp, 1 square centimeter, 100 megahertz, 28 dB microwatts per meter. Now we're going to the cables. On the other side, we have a cable, connection cable, 1 meter long, 0.8 microamps of common mode current. If that's differential mode, this is common mode. So we have a common mode current running through this cable, ECM of 0.8 microamps. And the same in this, if you put in this equation, you will get the same value, 26 microwatts per meter. Well, that's not a very nice anymore. Now we have a cable of 1 meter long. A very small current running on it would exactly do the same as 1 square centimeter of loop in the PCB. Why is that not so nice anymore? Well, check out this picture. These are the limits of the standard called CES-PR '25, class 5. That standard has class 1, 2, 3, 4, and 5. The 5 is the most rigorous level, and that CES-PR '25 holds for automotive electronics. And the limits for emission noise are, where is 28 dB? Here is the 28 dB microwatts per meter. So our electronics made like that would be already not passing, violating the EMC standards. See, 28. Here the limit is at 23 maybe. 4, 2, 22, 24, 20. Yeah, so less than 22. Here is 22. Here is 24. So 1 milliamp, 1 square centimeter, already violating CES-PR '25 standard. All right. So here I show you the spectrum of the digital signal. And as you see, the fundamental frequency, we have a spectrum which is flat, then the first corner frequency defined by the on time of the signal, following the 20 dBs per decade, and then to the corner value of defined by the rise time, then it follows 40 dBs per decade. Now, as I told before, this is proportional to 1 over frequency, and this is to 1 over frequency squared. So if I now put the frequency dependence of the differential mode signal, as you can check before, it's a f squared. So the differential mode electric field at a certain distance would rise with the square of the frequency. And if we now multiply these two, so this is the source frequency and this is the consequence frequency dependency. And if we multiply them, you will see that now here it rises with the square of the frequency here. So 1 over f squared, here is 1 over f, and here is constant. So this 1 over f squared and f squared cancel here. So differential mode noise would actually be frequency unlimited. But of course, there is a nice thing, because this signal is not perfectly trapezoidal. It has some, more or less, some shape which is curved, which means that there would be upper frequency going down even with the higher 1 over f3 at some point. Therefore, this would be then limited as well. Okay, what about the common mode? Well, common mode increases linearly with frequency, which means that it would have shape like that. Frequency limited. Oh, luckily. But we'll see if that actually holds till the end. Now let me show you some examples. And these examples I will show you in few real and imaginary examples. So a differential noise source is shown on a PCB or represented on a PCB as a current loops. So if there are connections between different ICs on that PCB, you would get a current loop, which will then be defined by its area, and that area would then radiate noise. And this is a differential mode interference on PCB. But what if we have a cable here that runs away from this PCB, and this cable has some common mode noise, common mode signal? Then it would radiate common mode noise. And the question now is how this common mode noise is generated. What are the generation mechanisms of this common mode noise? By knowing these generation mechanisms, you will be able to minimize them. And that would be a good opportunity for you to start with the EMC on the right side at the beginning of its origins. This is an example of a current-driven. There are two mechanisms. One is current-driven and the other is voltage-driven. So this is an example of current-driven mechanisms. So current-driven mechanism, which acts, as the name suggests, is a consequence of the current. So the current is flowing in a loop, starting with the noise. Let's say this is not noise source. This is more a signal source, a sort of a signal that is generated in the PCB by some, I don't know, digital or any other sources. This could be a communication signal between two chips, for example. This is the source and this is the load. So we have some impedance of the line. Usually that impedance of the line is very small, so it tends to go to 0. And then we have some load impedance. Usually loads in digital circuits are more or less high impedance, so these are really large values. But it contains some capacitances which might be decreasing this impedance at high frequencies. Then we have a return current back, and this return current runs usually on ground. And this is a ground which is also representing a kind of an impedance as well. So ground is not optimal, it's not ideal, it has some impedance as well. And usually what we care about the ground impedances are the inductance part of the ground impedance. The forward impedance, the impedance of a connection line, is even larger. So Z forward is larger than the Z ground. So it's not going to 0 if I'm very, very precise. It's even larger than the Z ground, but we don't care about it that much because the different parts of the PCB all contain ground. And ground has a large area as well, because all the PCB has some ground and everywhere. And this ground, because it is forming a large area, has a nice capacitive coupling because the areas of the capacitors are large. Therefore, this capacitance through the ground, from different parts of the ground through the air, is representing a common mode noise paths. The third path, which I was talking about. Now, how this current is generated? It is generated by the voltage drop on this impedance of the ground. Because the current is flowing through that impedance, That voltage drop is then generated, and this voltage drop, which I call the common mode noise voltage, is then running the current, generating the current through this common mode capacitance. Here are the equations. So differential current here, EDM, that runs on that line and then returns back on the ground to the source, is equal to differential mode voltage, which is a wanted, this is a desired voltage. We need it because this is making my PCB working. This is a useful signal. It's running through this line here and returning back here. So the current that is driven, the differential mode current, equals to voltage divided by the sum of all impedances. Then the voltage here is the current times Z ground, and the common mode current here is equal to impedance times the voltage. Admittance of the capacitance. This is the epsilon Cm, the admittance of capacitance. Now, if we simplify that a little bit, we say, okay, here on the ground, we are mostly discussing the impedance of the inductance of the ground. Why is that? Because usually the ground is, or every line on the circuit can be represented by at least a resistance and inductance. Well, at high frequencies, the inductance prevails because resistance is almost zero, but yacht omega L would increase quite quickly. Therefore, we say the ground is mostly inductive nature. Then we have the load, which I can maybe just change to resistance. So the load is represented by a resistor. And the Z forward is neglected because the resistance is much larger than Z forward. Now, that common mode noise that is then derived from these assumptions is this one here. And it contains square of the frequency, which again is very, very nasty. Now, going back to the case which I just telling you here, even though the common mode noise here is decreasing with frequency at high frequencies, if we take into account just the spectrum of the digital signal, the amount of that spectrum increases with frequency here, actually is more or less flat, so it will go actually upwards. But in the real case, it is again frequency limited. So going further, you see that there are three actual frequency dependent mechanisms. The first is the spectrum contained in the signal itself. Then it is how this signal, differential signal, is transferred to common mode noise signal, and there we have the square of the frequency. And then how this signal then radiates, and we have another frequency. So we have frequency to the 3. Yeah. So that's why we are really trying to minimize the frequency content of the signal, and therefore we are taking care mostly about the high frequency part of the source, and we want to avoid it as much as possible. So how is that actually performed in reality? If we have two components on a board that are communicating with a fast digital line, then the return current here that runs through this common mode impedance of the ground defines, or it causes, a voltage drop between different parts of the circuit. This is a common mode noise voltage. And that actually acts as a source. This is a source generator. On one side, let's say it's grounded. This doesn't concern you. On the other side, we have a cable that runs somewhere to another part of this setup. Let's say it goes to mouse, computer mouse, for example. Yeah, that could be an input of computer, a USB input, and that would be a cable to the computer mouse. And this generator generates high frequency signal, and this acts as antenna and radiates a lot. So this is common mode noise. It is current generated. The current in the PCB generates common mode noise. And this then returns back to the source on the third path, not through the cable wires. Another example. How can you minimize it? And here is an example how not to. Because we have the same thing here. We have generation of common mode noise. So we have some voltage difference. I can type it as denote this as delta U on the ground. That voltage difference then generates a signal that radiates through this cable. So we have a problem, and we put this device into the SIQ laboratories, and they measure this and they say, okay, it's radiating too much. But what is the cause of that? Is it common mode noise or differential mode? Well, we say, okay, we'll use a better cable. Okay, we use a cable that is shielded. It is a coaxial cable or a microphone cable that has a very good shield and two wires. So better cable, and what does the better cable do? It actually, if we have a differential mode noise problem here, then this differential mode noise would then couple to this shield, and it will be transferred back to the ground. So it will be well shielded with this shield. But what if it is a common mode noise problem? Then the common mode noise current would run in the same direction, and the cable shield would have no effect on it. So by knowing from the beginning that it's a common mode noise problem, we wouldn't apply a shielded cable because it will have no effect. So that's importance, first of such examples of importance of knowing what kind of problem we have. Another option, another way of generating common mode noise is a voltage-driven common mode noise source. This is quite simpler, much simpler than the first one, because it contains just a single voltage generator, and this is a differential voltage generator, which could be again something that changes voltage very fast in time. Anything in the circuit where the voltage changes really quickly. It could be a transmission line between two circuits. It could be any voltage node that has a high speed signal on it. And let's say this is a bottom track of your PCB, and this is the top track. This may be also a ground plane, and this would be a track on top. And now these two copper areas, so this is the top layer and this is the bottom layer. These two copper areas have a common capacitance between because they are close to each other. And actually this differential current then runs here. The voltage change here between these two tracks is also running some current through the air, because the air also represents a certain common mode capacitance. So this common mode current is just simply a consequence of the YCM and the differential mode voltage. And how to minimize that? Well, you have to minimize this common mode capacitance. How you do that? Well, one thing you can do is you can just take the line towards the middle of the PCB. So instead of putting that line at the edge of the PCB, you can put it inside, away from the edges. And therefore the electric field would be confined within the circuit, not radiating far away. like that. Yeah? And in order to contain 98%, so only 2% of leakage, you have to use 100 times the thickness. If this is the thickness of the PCB, then 100 times of the thickness would be really a lot. In terms of the classical 1.6 millimeter thick PCB, you would need 16 centimeters. Or in case if we want just to save 70% of the field and 30% of leakage, you would do the 20 rule, so it would be 3.2 centimeters. Well, that's a lot. I mean, that's really a lot. But what can you do? Well, the other thing is decrease the thickness. Okay, decreasing the thickness would mean that your PCB now, maybe if it is a 4-layer, you can afford it. Having the mid part very wide and this very, very close together. And here you have ground. And here you have ground. So now the lines on top and on bottom here are very close to the ground. So you're decreasing the thickness and therefore you're decreasing the radiation of your noise. So that's one of the reasons why these PCB stacks are like that. That they do have a wide mid part and very narrow or very small distances between the two outer layers. Now, you have to identify now these parts in order to make them better. So let me go now to the example that you have been working lately on the lab course. On the lab course, you've been working on a very, very simple LED switch mode power supply. And I'm sure that the assistant explained to you how it works. But nevertheless, I would like to do it also here. And let me do that. I was telling you about. Maybe like that would be sufficient, yeah. So here, what I'm showing you is the schematics of this lab course circuit. So first of all, we have to understand how it works. Well, how it works. If this is the input, here I have the battery voltage. A single battery of, let's say, battery, let's say 1.5 volts. Here I have an LED which requires at least 4.5 volts. So I have to boost the voltage. And for that I have this coil here. And how it works, when the switch is turned on, the current flows from here through the transistor and back. Now on the coil we have voltage like that. In the coil there is a current and the energy of the coil is equal Li squared half. Now the current that builds up here, then when the transistor is switched off, runs, this is the first case when the T is on, and the second case is when the T is off. Then the transistor in the second case turns off and the voltage on the coil switches immediately. Why? Because it has to maintain the energy. The energy is the only thing that does not change abruptly. Therefore, the voltage has to change in order to keep the current running. And therefore, when the voltage changes, the current flows through the diode and through the LED diode back. Why does it flow like that? Because the voltage now here is the sum of the input voltage, battery, plus the voltage on the inductor. UL2, UL1. Now the voltage here is 4.5. Here we have the voltage on the diode, so it might be around 5 volts here, approximately, since we have voltage drop on the diode. Forward voltage is that. Now, the question is, where are the critical parts of this circuit? Okay, we'll start with current loops. Where are the current loops which are the most important in terms of high frequency content? First of all, the current through the coil cannot change immediately. The current, when the transistor is turned on, will rise, and the slope of the rise will be proportional to 1 over L. And when the transistor is turned off, it will drop. Again, the same, not the same, I would say not the same, but similar slope. So the current through the coil is continuous. Well, what about the current through the rest of the parts? The current through transistor will rise up, and when the transistor turns off, it will immediately drop to 0. And then it will be 0 for some time, and then it will rise up again, like that. The transistor is a switching device. Therefore, it has very, very fast switching parts. What about the diode? The diode, when the transistor is turned on, the current through the diode is 0, because we have 4.5 volts here, and here we have 0. When the diode turns on, when the transistor switches off, the current would immediately jump up, and that it will follow the coil current, and then 0, jump up, following the coil 0. So again, through the diode, we have very, very fast changes of current. So all the switching elements that are here are actually forming high frequency currents, because these parts, which I just colored, are the most important ones. Where do they actually exist? That one exists here in this vertical part of the circuit. That one exists until here, because now if the capacitor is high quality capacitor, it will have DC voltage on it. The voltage on the capacitor will not change quickly, it will change slowly. And that high frequency current would run through the capacitor, not through the diode. Here I have DC current. But if transistor is not well placed, and for that reason it has some series inductance, that would cause large voltage drops on that inductor, which will be then transferred to the diode. So if the capacitor is really good and well placed, we are concerned only about the current loop, which I will just draw now. This is the current loop we are concerned. Here, 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 and here. And this is the area which we have to take care. That's the area we have to take care in our design. This is regarding differential noise. What about regarding common mode noise problems? There we have two problems. We can have current generated or voltage generated common mode noise. Current generated common mode noise, as the first one, is here, running through these loops. And where do we have AC current, high frequency current? From this point to this point here. So here we can have on the ground voltage drops of common mode noise, which would then be generating high frequency interference. What about the voltage generated common mode noise? We can have to find the parts which are containing high frequency voltage changes. Where are they? Here we have a capacitor, so surely here on the capacitor the voltage does not change quickly. Here we have a capacitor. Here also the voltage doesn't change quickly. We have DC voltage. So the only part where the voltage changes quickly is here. This is the switching node. I will name switch. Switching node has high frequency voltage changes. Why? Because when transistor is switched on, the voltage here would be almost zero. When it is switched off, it would be in range of 5 volts. And that, now I really don't have space to draw, maybe I will draw here. Changes 0, 5, 0, 5, 0, 5, very quickly. So I have common mode noise voltage generation here. Now I really did a lot of drawing here. I hope that you followed. Now let's go to the PCB. That's the PCB. One of your designs I just took. So what do we have here? Let me show you the current loops first. Starting with the input capacitor, going through the coil, okay, not a big problem because the current through the coil is continuous. But where is the loop which defines the high frequency part of the currents? Where the high frequency parts of the currents are? They are here. Now, where is that? From transistor, diode, capacitor, output capacitor, and back to the sense resistor. Let me follow that path now. From transistor, which is here, transistor is here, okay? Through the diode, back to the capacitor, again, transistor, diode, back to the capacitor, to the ground, back to the sense resistor, and back here. That's the size of the loop. Now you can imagine, can it be smaller? Think about it. Try to minimize it. Maybe you turn components a little bit around. We'll try to do that. What else? Another thing is the common mode part. Let me show the current generating common mode voltage. It starts here. Maybe just previous picture. It is from here to here. Okay, so the common mode starts here and ends there. So this is the place at which the voltage drop on the common mode part of the ground would then cause generation of noise. So the impedance of this part should be decreased. How you can do that? Well, you can put these 2 points as close as possible together. And then you would have smaller impedance of this ground. Or you can make the track wider. Or you can have another track on bottom layer. So all that can be done to make the noise generation of your impedance of your circuit smaller enough. Because here you will connect the cable which will go to the battery, and that would then cause an antenna to radiate this noise here. What else? Oh yeah, we have the voltage noise generation as well. The voltage noise is generated by the switching node. A switching node is this part here. So the whole connection between the coil, the diode, and the transistor. Let's go there. Coil is here, so this part is a switching node, diode and transistor. So all that is a switching node. Maybe I can draw it again. No, I can't. So that part is a switching node part, which has to be minimized, and remember, it has to be kept away from the edges. So putting this to the edge is not a wise idea. You should put it as much as possible away from the edge. But there's not a lot of space, isn't it? I mean, here the coil is just at the edge, but you might just turn it for 90 degrees and then this part would be deeper into the PCB. The area of that switching node should be as small as possible. Let me maybe now show you what I would do with this circuit, just try it. I will do it for the first time. I will not actually, I did not prepare for that, so please bear with me. I will maybe switch now. Okay, like that. So I will try to do my best. First of all, I would like to put these 2 points as close as possible together. Maybe just to remind you, the output on the diode should be, so this area here should be as small as possible. Therefore, you should make it smaller by taking the line from, or the track from this capacitor. But not only that, it should be also containing no high frequency currents. How can you do that? Well, taking the voltage to the LED diode from the most calm part of the voltage you can find, and this would be apart from the capacitor. So I would do it like that. And here on the ground I would do it as well. Like that. Now this is totally fully DC current here. No AC part which is a part of that line. Further, maybe to put these, to make this connection between the, or to make this part where the common mode current is generating common mode voltage between the source and the load, this part here should be shorter. So maybe I will just change it a little bit, put that one upwards like that, and move this transistor in that direction. You see, now this part, this is a resistor, now this part is much smaller. I can even make it even smaller. Now I could actually put it more closer to the edge. Let me see if I can do that. No, I can't actually. That's not even a good idea right now. Let me do that in another way. That's really not, okay. Maybe like that. Maybe there is a problem also here. I would have to do it like that, probably, yeah. I would probably try to use as much of the current loops as possible, yeah. Not finished completely here, but let's say I would prefer of not making current loops on the ground, but I will maybe correct that later. So now I made this area really small, so the impedance of this ground is larger. I can also make it wider, like that. Or even, I wouldn't really do that. I would probably use ground planes anyway. So I will probably go to ground planes. So I will go back to the normal width of the line. What else? Now the switching node. Maybe I would try to rotate it a little bit and put it more in the center. And by that also making it smaller. How to say, the area of the switching node should be as small as possible. And it should be contained in the middle. So this is the switching mode area. Now it is placed in the middle, as close as possible. Now let me check this new design. The switching node is in the middle. The area of the loop which is actually containing high frequency current is this one here. From the transistor upwards, diode back, output capacitor here back, and further. Now, what can I do more? Well, of course, I can put some planes. I will actually make a polygon pour on top layer, and I will choose the ground net to use it. Okay. Now that polygon pour should be connected to the same net, all net objects. So I will select that one and I will re-pour it again. Okay, now it is very well placed and connecting everything. You see the thermal reliefs here for better soldering. What else? You can, instead of using a 2D design, like here, when you have the current loop, which I just showed before, here, upwards, there, here, and back, and so on, you can actually use the bottom layer as well for that. So I will now draw a bottom layer, placing polygon again, here, here, down, and back. I have to connect it to ground, and I did. And what I did with it actually is shield the bottom layer of the PCB, and as such shield the PCB from the capacitive coupling of the noise. Now we have a bottom ground layer, but that bottom ground layer will not help if we don't allow the currents to return on them. So every ground pin that we have to be connected to this bottom ground layer, like that one. Let me make it smaller. There is no rule here in this design for smaller wires. Okay, I will put them as they are. What else? Here. Maybe I will put a wire in between. Maybe I will put it here. And there. Maybe I can make smaller wires, which will be also useful. So I will go to design rules. In design rules, I will actually make wires smaller. So I will go to the routing wire style, and I will choose minimum of 0.9 maybe, and maximum 1. Maybe I will use diameter 0.6, yes, 0.6, 0.8 and 0.9, 0.7 preferred, and hole size would be 0.3, 0.5 and 0.4. These are typical dimensions for a PCB that are not violating the rules of the wire inner ring and the width of the diameter of the holes. Find similar objects, and thus I'm trying to find all the wires. Okay, and I will now choose another diameter, 0.6 and 0.3. So now these wires are small enough to be used anywhere in the design, let's say also here. So putting wires to connect to the bottom layer is essential for the device to be working also, so that the bottom layer is also acting as a good conductor for current. And therefore the current loops are no longer also on top, but actually the current is also flowing on bottom layer. And the area this current is actually taking can be much smaller then, because the area which they take actually is the thickness between the top and bottom layer. And in the meantime, yes, I must say, the designer of this circuit, which I took it from, did not set correct layer stack. So we have to set it up. Maybe it was, I'm not sure right now, maybe this PCB is just too small and therefore the layer seems to be thick, but we'll check it out. Anyway, using bottom layer for return currents is very advisable. Yes, it's correctly set. And therefore, yeah, going to the 3D again, you have current flowing on top and then returning on bottom, and that would be then the width, the thickness of the loop, the area of the loop, top and returning on bottom. And by using big and wide current copper planes for current also decreases its impedance. So I would actually go and say use more wires just to make the connection between the components better, so that the connection for this current to run has lower impedance and therefore better connection, lower voltage drops on it. So by using good connection, you can have lower differential to common mode noise conversion. Now all that which I just shown, what is still missing? Maybe what is still missing? Nothing really. Maybe cooling of the diode, but that's another thing. I will not go into this right now. So what we ended with: switching node in the middle of the circuit. The high current loop, which contains high frequency currents, is running very, very neatly, being narrow as much as possible. The point where you have the high current loop running on the ground back, where you have the high current spikes, it's between this point and this point, which is very short. So by that, you are not causing common mode noise problems. And that's it. I think I did as much as I could. I couldn't do more. Maybe you have some ideas how you could improve that design even further, and let me know. So let me wrap up this lecture just by a few other slides. One of the problems with the switching of the transistors is also that they heat up quite easily because they are high power elements. They are switching high currents and voltages. Therefore, you have to cool them down with some capacitors, with some heat sinks. And heat sinks, well, they are a nasty thing because the heat sink is increasing the area of these devices. And heat sink then can act as a nice common mode noise spreader. Nice increase of capacitance to spread common mode noise. Voltage driven common mode noise, if we just put a heatsink, would then increase it. So if we would put a heatsink here on this transistor, but we wouldn't do that, of course, because that transistor is a low power transistor. But if we put a heatsink there, we would increase the area and therefore we would increase also the radiation. Now, how is that possible? Usually heat sinks are not in direct electrical connection to the device, but actually if they are put really close to the device because they want to dissipate heat efficiently, and there is a very, very small distance between the voltage changing part of the device and the heatsink, and this capacitance then here is transferring the noise to the heatsink, and the heatsink then radiates it around. So this was all about the noise sources. We discussed the type of the spectrum of the signal. We discussed the common mode and differential noise, and we discussed how these noises, the common mode and differential noises, are then generated in the PCB. Now, what about immunity? Immunity is also a part of the EMC. So in the immunity, we say that if we make a PCB that is emitting really low, it will be also very immune. In most cases, that's true, but there are some which is also not the case. But let's start with the coupling modes. As we all know already, the we have common mode noise and differential mode noise. And also coupling of external noise is similar. The noise can couple in a way that it generates voltage between one and another line on the connection between two parts of the circuit, or it can generate a voltage between the line and the ground on that circuit. That would be a common mode noise voltage. Or it can also change the potential of the whole device as it is. That would be called antenna mode, coupling mode. Well, why is that important? For example, if you have a differential signal, what does that mean? That the voltage is defined between two lines is defining the digital information or analog information. So the information is defined by the voltage between these two lines, two differential lines. If the voltage with respect to the ground changes, then it is not affecting this differential voltage, which is a good thing. So using differential signals in your design will be very beneficial for noise coupling. Now, still there is a problem if the noise couples differentially. But the area of that loop, if you keep it really, really small, then the noise will not couple much. So if the noise couples like that, it will only affect the common mode part. And if the circuit is made in a way that the common mode part is intact, it will not affect the signal. The antenna mode usually does not affect the signals inside if they are not, again, transferring from one to another. Well, that's a strange thing, right? How do differential and common mode noise transfer into each other? How do they transform into each other? Let's go to the last slide of the lecture, that one. Oh, that's not the last slide. It's the one before last. The last but not the least would follow very soon. Here is an example of the same input where you see that there is a load resistance here and there are two common mode resistances or impedances actually. And these are connecting each of these inputs to the common mode ground. So what happens if these two impedances are different? If these two impedances are different, then you have a problem. Because if you have a common mode noise that is coupling to the circuit, it will affect the differential voltage as well. How? Usually your information is transferred from one part to another using differential voltage. Now this differential voltage is then transferred to inside of the receiver, which is represented by this load resistance, and the information is safe. But if you have a common mode noise that is coupled to these two lines in the same direction, if there were these two stray impedances, it would not affect it. The voltage will not be changed. If there are two of these stray impedances, if they are the same, then the voltage on them would be also the same, so the information will not be affected. But if they are different, then the voltages are also different. So these two voltages and that one is then affecting the electromagnetic interference voltage we just talked about. And that one changes the differential voltage and you measure it. You actually see it in your measurement. And that's not good. So you can keep these two impedances similar, but you don't have always the means to do that, because these can be unintentional impedances. Some impedances that are formed by the surroundings in the circuit due to the geometry, not due to the actual component that you put there. Because you might not put anything, but there would be there as a stray capacitances and stray inductances. So, final slide for today. Example. Usually when you have very low signals to measure, you use amplifiers. And the best amplifiers you can get are instrumentational amplifiers. Instrumentation amplifier is a very, very good amplifier that can have gains more than 1,000 or even more, and it has really high common mode rejection ratio, which means that it will actually amplify only the differential part of the voltage, not the common mode part of the voltage, which means if I just draw it here, it means that actually it will just, if the voltage is like that on one line and like that on the other, the actual voltage that will be applied would be the difference between those two. So the common mode part and the differential mode part are here, and the common mode part will not be amplified. So, good. But what if a part of the common mode noise is transferred to differential by the means of the previous slide? Then you have to make sure that your impedances towards ground are the same. Okay, so here, come on, where is my mouse? Here. Here. So, here the common mode current runs in, and if you have the same resistors, let's say, applied to this input, why do you put these resistors in the first place? That's maybe a question also that requires an answer, is that you have to provide a DC path for the bias currents of this amplifier to the ground. And they say, okay, if you have a certain microphone to amplify, you may use two resistors of the same kind, and that's it. Then you have stray impedances to ground the same for both cases. If you have a thermocouple, okay, it's very low impedance device, you might only use one resistor. But what if now the common mode noise is coupled to the wire, which runs for 10 meters maybe, and then you have different impedances here? Oh God, then you have a problem. And here is an example of a design of a student of mine who did an input for the thermocoupler. So he wanted to filter some noise already at the beginning. So he made a differential filter, that resistor, that capacitor. This is differential filter, and these are common mode filters. So he's filtering common mode noise and differential mode noise here, because he used really long wires here, and there are high frequency and high power motors in nearby, because he's measuring temperatures of motors. Therefore, he did it to filter this noise. But then how he placed this filter, he did it in a way, these are bias resistors to keep the common mode voltage stable as much as possible. He made this filter totally symmetrical. There is one line, this is the other. So these are all symmetrically placed components till the input of the amplifier. So everything is symmetrical, including these values of resistors and capacitances, but also the placement of these components in order to make the design equal for left and right part. So these two stray elements towards the whatever there is are the same. And that's how he made sure that any common mode noise that might couple into this thermocouple would be equally taken away on each side of the input of the amplifier, and therefore also the differential voltage noise will not build up. So to sum it up in this at this stage, I must say that designing your designs fully differentially and symmetrically at the point where you have problems with you accept or your problems are likely, where you have very high chance of getting a noise into the circuit, such as input amplifiers, which are very sensitive, as I said before, you have to take care that your design is totally symmetrical in any way. And that would keep your immunity on a high level. If you have a single-ended inputs, which are all defined toward ground, then you cannot do that. So if you want to be really immune from the external noise sources, you might go for differential design. And this is also a choice you make at the beginning. And later on, if you find problems with that, it's too late, because you have to go back to the drawing board, which might not be possible anymore. And let me conclude now this lecture. I hope that I was not too long. After this lecture, you should be able to know what is the spectrum of the signal of idealized digital signal, identify critical sources and sensitive parts of the PCB, calculate the amplitude of a common mode and differential mode noise. If I give an example of two currents running in a line, that you calculate the influence of that common mode signal to the differential, so that you know how you can how a common mode noise can be transferred to differential, which is then acting as a noise source. And you should explain and the origins of common mode noise and differential and its impacts, how they are generated, how you can then minimize them in a proper way in reality. So there are some chapters in book you can also refer to. And yeah, I'm looking forward for your consultations, and see you next week.